Alright, in this video we're going to take a look at three different solubility equilibrium problems from the supplementary problems for this unit. So the first one, question 18, is a sort of straightforward solubility problem. You're asked to calculate the mass of iron hydroxide that you need to make 500 mils of saturated solution. Remember that a saturated solution is one where you have solubility equilibrium. We're given the equilibrium constant, the solubility product constant, Ksp, at 7.9 times 10 to the minus 16. So this is a typical solubility problem. It's got two basic steps. In the first step, we're going to use the Ksp, an ice table, straightforward equilibrium calculation. We're going to find the solubility of the salt. Then we're going to take the solubility and the volume, and we're going to go find the mass of salt that can dissolve. So let's jump in. Write yourself a balanced equation. Now, if you think you know what you're doing, pause the video and just go try it yourself. So you have iron hydroxide, FeOH2, and it's a solid. It's going to dissociate, break apart into its ions, becomes Fe2+. Now I know it's 2+ because each hydroxide is -1, and there's two hydroxides bonded to the iron, so the iron has to be 2 positive. That's aqueous, and then the two hydroxides, and they're also aqueous. Alright, so now we'll do an ice table. The iron hydroxide is a solid, so just like liquids, the water and the acid-base unit, we'll just put a big X under it. If the question doesn't say otherwise, we assume it's being dissolved in water, so iron concentration would initially be 0. There's no iron in pure water. There is some hydroxide in water. The water's hydroxide concentration starts off as 1 times 10 to the minus 7 molarity, but we'll assume that that's so small that we can ignore it. Sometimes, as we saw in class, that does lead to a problem, but usually we can ignore the hydroxide. Now the iron, as the salt dissolves, the iron's concentration and hydroxide will both increase. If this were the equilibrium unit, we would just say increases by X and 2X. But here we're going to use a slightly different symbol. We're going to use the letter S. And the reason I'm using an S is to connect the concentrations of the ions to the solubility of the salt. The 1-to-1 ratio between the salt and the iron in this equation tells me that the concentration of iron in the saturated solution will equal the number of moles per liter of the salt that dissolved. In other words, iron's concentration is the solubility of the salt. The hydroxide concentration in the saturated solution is 2 times the solubility of the salt. Let's write our equilibrium expression. Ksp equals concentration of iron times hydroxide concentration squared equals, 7.9 times 10 to the minus 16. Now, that's a very small Ksp, so this salt's going to have a very low solubility. And that's equal to S times 2S squared, just substituting from the equilibrium line of the ice table into the Ksp expression. 2s squared equals 4s squared, and when you multiply that by the s in front, you get 4s cubed. So the Ksp is equal to 4s cubed. Then S, the solubility, will equal the Ksp, 7.9 times 10 to the minus 16, divided by 4, and then cube rooted. Now there's more than one way to write the cube root symbol. You might in a math class write that, cube root, but remember that cube rooting means the same thing as raising to the power of 1/3, and that's how I like to write it. So raised to the power of 1/3. Now I'm grabbing a calculator. 7.9 times 10 to the minus 16 divided by 4 equals, then on the calculator, raise that to the power of 0.33333 repeating. Use about 4 or 5 threes there. Keep in mind that 1/3 is 0.333 repeating. So when I do that, I get 5.8 times 10 to the minus 6. 5.8 times 10 to the minus 6. And that will be moles per liter of the iron hydroxide. Now notice that also means that the iron's concentration is 5.8 times 10 to the minus 6 molarity. If I wanted to know the hydroxide concentration and perhaps find the pH or pOH, I'd have to double this value to get the hydroxide. Now the question wanted to know what mass of iron hydroxide would dissolve. So let's take the volume, 500 milliliters. And I'm going to use unit multipliers, but feel free to use the formulas. C equals N over V, and then moles equals mass over molar mass. So I'm going to take the volume in milliliters. I'll get rid of milliliters, switch to liters. I'll get rid of the milliliters, sorry, the liters. I just did the milliliters. So I'll get rid of those liters, and now I'm going to switch to moles of the iron hydroxide. Now you might wonder, how are we going to do that? Well, the solubility is 5.8 times 10 to the minus 6 moles of iron hydroxide per liter. So that will be the solubility of the salt. And then we'll get rid of moles of iron hydroxide, and we'll switch to grams of iron hydroxide. And of course, that's the molar mass of the iron hydroxide. So 1 liter, 1,000 milliliters, 5.8 times 10 to the minus 6 moles per liter. And then the molar mass of iron hydroxide, grabbing a periodic table, is 89.87 grams. 89.87 grams per mole. So now, picking up a calculator and evaluating this, we get 2.6 times 10 to the minus 4 grams of iron hydroxide. And that's how much iron hydroxide can dissolve in the 500 mils of water using the solubility and using the molar mass of the iron hydroxide. Alright, in this next video we're going to take a look at question 20, which is a totally different problem. This question is a new topic in the unit for us. So we're told that lead iodide is a bright yellow precipitate, so it's not very soluble in water. It's got a KSP of 7.9 times 10 to the minus 9, so that confirms for us that it is something that's not very soluble. And then we're told that a chemist took a gram, 1.00 grams of sodium iodide, and sodium iodide, of course, contains iodide ions, and then added that to 2 liters of 0.1 molar lead nitrate, and the lead nitrate, of course, contains lead ions. Now, when you mix sodium iodide with lead nitrate, you can imagine a double replacement reaction happening, and it's quite possible that lead iodide would form. And the question is, will we observe a precipitate in this situation? Now let me just jump in and show you how to do this. Write the balanced equation for the dissociation of the salt that might precipitate. So in this case, lead iodide, PbI2, is the thing that might precipitate. And if there were solid lead iodide, it would dissociate in this way. Now, why am I writing this equation? After all, we're wondering if we'll be forming lead iodide, not whether or not we'll be dissolving it. The reason I'm writing this is because the KSP that was given is based on this reaction, right? That's the KSP for lead iodide, so it's based on lead iodides dissociating in water. Now the question, will we see the precipitate form? Will we see lead iodide solid? We can now translate that question. Notice that lead iodide solid is on the left side of our equation. So really what we're wondering is, does this reaction that we've just written, does it shift backwards? That's the question. If it shifts backwards, we'll be forming solid lead iodide. Yes. If it doesn't shift backwards, then no, we're not going to see solid lead iodide. Now, back in our equilibrium unit about 5 or 6 weeks ago, we learned how to predict whether an equilibrium would shift forwards or backwards, or perhaps it doesn't shift at all. Maybe it's at equilibrium. The way we talked about doing that a few weeks ago was to calculate the QSP value. So QSP, we were just reminding ourselves, stands for the reaction quotient. That's what Q stands for. And we know that it's calculated the exact same way that you would calculate Kc, or in this case, KSP. The equilibrium constant and Q are calculated the same way. The difference between Q and K is that for Q, we can put any concentrations we want into the expression. For K, we have to put equilibrium concentrations. So one thing that you would use Q for would be just to determine if you're at equilibrium. If you calculate Q for a reaction system, and it turns out that Q is equal to Kc, or in this case KSP, then yes, you're at equilibrium, and in this context, you would have a saturated solution. But if Q is not equal to K, in fact, if Q is greater than K, we showed in the equilibrium unit that that means the reaction would shift backwards. So when Q is bigger than K, we see a backward shift. Now, why is that? That's because Q would need to get smaller in order to come to equilibrium if Q is bigger than K. For Q to get smaller, you would need less lead and less iodide. Those are the products in the reaction, so it means you need less products. To have less products, you'd have to have a backward shift, and you'd form some of that solid lead iodide. So now we see a little plan. If we want to know whether the chemist will observe a precipitate, we need to calculate Q. But to calculate Q, we need to know the lead concentration and the iodide concentration, which we'll square. And then we'll have the value of Q. So let's do that. Do we know either the lead or the iodide concentration? Well, the solution was 2 liters of 0.1 molar lead nitrate. Now you are adding 1 gram of salt to that, so technically the volume will change, but putting a gram of salt into 2 liters of solution, we can pretty much assume that the volume is constant. It's essentially constant, which means our lead concentration, if it was 0.1 molar lead nitrate, there would be 0.1 molar lead, and there'd be 0.2 molar nitrate. 0.2 because there's 2 nitrates in the formula. So the concentration of lead in our system is 0.1 molarity. Now what about the iodide concentration? The question didn't tell us that, but it did tell us that we've added 1 gram of sodium iodide to the 2 liters. So we can just go and calculate the iodide concentration. We can take the 1 gram of sodium iodide, and we can convert grams to moles of sodium iodide. And then you might do this next unit multiplier just in your head, but instead I'll show you it here in the video. We'll get rid of the moles of sodium iodide, and we're really interested in just iodide, so let's switch to moles of iodide. But I don't want moles, I want concentrations, so finally let's just divide the moles by the liters, and then we'll have moles per liter, which is concentration. So the moles of sodium iodide with grams, that first unit multiplier, is a molar mass. So 22.99 sodium plus 126.9 iodine 149.89 grams is the molar mass. The second multiplier is based on the stoichiometry of the formula sodium iodide. There's only one iodide in the formula for sodium iodide, so you'd have 1 mole of iodide for every 1 mole of sodium iodide. Notice if we were doing the same thing for lead iodide, look at its formula, we would say that there's 2 moles of iodide for every 1 mole of lead iodide. But in sodium iodide, there's just a 1-to-1 ratio. And the volume was 2 liters, right? The question said above, we have 2 liters of the solution that we're dissolving this in. So let's take the 1 gram, divide by 149.89, times by 1, and divide by 2. We get 0.0033, or 0.0034, if you round it off properly. I guess we need 3 sig figs, right? So 0.00334, and that'll be moles per liter, or molarity, iodide. So now we can put that into our QSP expression, 0.00334 molarity. We're going to square the iodide and multiply by lead concentration. So 0.00334 squared times 0.1 is 1.1 times 10 to the minus 6. 1.1 times 10 to the minus 6. And that's the value we got for Q. Now the question was, will the precipitate form? Will we observe this precipitate forming? And we agreed that if Q is bigger than K, then yes, you'll see a precipitate. So we can say here, down at the bottom perhaps, notice that KSP is 10 to the minus 9, QSP is 10 to the minus 6. So since the QSP is bigger than the KSP, we see a reverse shift in the equilibrium. And of course that means we'll have solid lead iodide forming. So we'll say precipitate, PPTE is my abbreviation, will form. Okay, so there's the result. The precipitate will form because QSP is bigger than KSP. Precipitate forms. If the QSP were equal to the KSP, no precipitate would form, and the solution would have been saturated, perfectly saturated with lead iodide. If QSP were less than KSP, in the equilibrium unit, we would have said that means a forward shift occurs. But notice here, there can't be a forward shift because that would require lead iodide to be present. There is no lead iodide. So if QSP were less than KSP, in this unit, we would simply say the solution's not saturated, and therefore there's no precipitate. So when Q equals K, saturated, no precipitate. If Q is less than K, not saturated, still no precipitate. If Q is greater than K, you might call that a supersaturated solution, meaning there's more ions dissolved than there should be, supersaturated, more than saturated, and therefore there'll be a reverse shift and a precipitate will form. Alright, this is the third and final question we'll do in this video lesson. This is question 21 from the supplementary problems, and it's again a slightly different question. We're asked here for the mass of potassium hydroxide, which we could dissolve in 500 mils of 0.2 molar magnesium nitrate without causing a precipitate to form. Now just pausing right there, if you think about mixing those two chemicals, you can imagine double replacement reaction happening, and you'd see that potassium nitrate might form, But potassium nitrate, according to our solubility rules, would be a highly soluble salt. It starts with an alkali metal and it has nitrate in its formula. Potassium nitrate would not be a precipitate. But then there's magnesium hydroxide. Hydroxide salts are usually insoluble. In fact, we see the KSP of magnesium hydroxide is very small. So the precipitate that might form in this situation is magnesium hydroxide. Now, if you simply notice that it told us the KSP of magnesium hydroxide, you'd notice that was a major clue designed to help us figure out what the precipitate might be. Now, this question, you might think you can just set up an ice table and go find solubility, etc. But this question is a little bit different. Notice we're going to add, let's just draw a little picture perhaps. We've got, in the question, we're told we have 500 milliliters of the 0.2 molar magnesium hydroxide. 0.2 molar magnesium, that's not magnesium hydroxide, magnesium nitrate. That's what's in the beaker. We're wondering how many grams of KOH can we add without causing a precipitate to form. Now, another way to have said that would be to make the solution perfectly saturated, right? So we're going to add enough KOH to just perfectly saturate the solution. Any more than that, and there would be a precipitate because you'd have a supersaturated solution. Any less than this amount, and it's still no precipitate, but you could have added more. So the amount of KOH needed to make the solution saturated would be the maximum amount of KOH that we could dissolve without causing the precipitate. Now, how do we do this? Well, let's write just the KSP expression for magnesium hydroxide. It has 1 magnesium and 2 hydroxides, so you could just write Mg2 plus concentration and hydroxide concentration squared. If you're not able to write the KSP expression by just looking at the formula of the salt, then write the salt's dissociation equation first and then get the KSP expression. So we're told that 7.1 times 10 to the minus 12 is the KSP, and notice we know that the magnesium's concentration is 0.2 molarity. So we know the KSP and we know the magnesium concentration. We're going to add some hydroxide, KOH. We'll assume that the volume stays constant in the beaker. We're going to assume that we add just a little tiny bit of KOH, and so the volume doesn't change, which means we don't have to worry about diluting the magnesium. Its concentration is 0.2. So notice that would leave one thing in this KSP expression unknown, and that would be the hydroxide concentration. Now, what would that hydroxide concentration represent? If we put the numbers in, we have 7.1 times 10 to the minus 12, the KSP, is 0.2 molarity, the concentration of magnesium, times the concentration of hydroxide squared. So what would this hydroxide represent? Well, if you stopped and thought about that, you'd realize this hydroxide is the maximum amount of hydroxide you could have with 0.2 molar magnesium to make the solution perfectly saturated, because in this case, Q would equal K. So let's calculate what that concentration is. The concentration of the hydroxide that you could have with 0.2 molar magnesium would be 7.1 times 10 to the minus 12 divided by 0.2 and then square rooted, right? We did the square root because the hydroxide was squared. So now we'll grab a calculator and evaluate that. 7.1 times 10 to the minus 12 divided by 0.2 equals, and then square root the answer. And you get 6.0 times 10 to the minus 6 molarity. 6.0 times 10 to the minus 6 molarity of hydroxide. Now we're just about done. The question was, well, what mass of potassium hydroxide could you dissolve in 500 mils of the solution? So we know the hydroxide's concentration, and we know that KOH is the source of the hydroxide. So let's go find out the mass of KOH that we could use. We'll start again with the volume, 500 milliliters of solution. We'll convert milliliters to liters, and now we'll use that concentration to convert liters to moles of hydroxide. But we're not really adding hydroxide, we're adding potassium hydroxide. So we'll get rid of moles of hydroxide and put in moles of KOH instead. Right? But the question didn't want the moles, it wanted the mass. So we'll get rid of moles and we'll switch to grams of KOH. Alright, so the logic again, we're converting milliliters to liters. Using the concentration we just found for hydroxide, we'll get the moles of hydroxide. Then we'll look at the formula KOH and we'll realize there's 1 mole of hydroxide for every 1 mole of KOH. And then the molar mass of KOH. So 1 liter has 1,000 milliliters. The concentration was 6 times 10 to the minus 6 moles per liter. 1 to 1, the hydroxide in KOH. And then the molar mass of KOH, 39.1 potassium plus 16 plus 1.01. I get 56.11 grams per mole. And then finally, grabbing the calculator and evaluating, 500 divided by 1,000 times 6 times 10 to the minus 6, and then times 56.11. So 1.7 times 10 to the minus 4 grams, a really small amount. 1.7 times 10 to the minus 4 grams of KOH. All right, so now stand back and think about this question before we leave it. So we were adding the KOH to the magnesium nitrate, but we wanted to add just enough KOH to not see a precipitate. We weren't going to see a precipitate. So that's the clue that we don't need to do an ice table. All we need to do is really think about the saturated solution, so the KSP expression. Then we realize we know the KSP and we know the magnesium concentration. So we put those in and we calculate the hydroxide. So hydroxide is equal to KSP divided by the magnesium concentration, square rooted. That's what I'm doing here. Then we get 6 times 10 to the minus 6 molar hydroxide concentration. So the question about how many grams of KOH, we'll first convert the volume to liters. Liters in concentration of hydroxide will give us moles of hydroxide, and then moles of hydroxide will be easily converted to moles of KOH. There's 1 hydroxide in KOH formula, so 1 mole of hydroxide for every 1 mole of KOH. Finally, we didn't want moles, we wanted grams of KOH, and that's what I've done at the end there with a unit multiplier. So there you have it, 3 different kinds of questions, a straightforward solubility problem with a small twist at the end in the first question. Then in the second question, the reaction quotient, and using it to predict whether you're at equilibrium, and if not, the direction you go to reach equilibrium. And then finally, this question, which is another tricky one, it does not require an ice table because we're not forming the precipitate. We're simply wondering how much KOH could we add before we see the precipitate. And the answer, as we found, is 1.7 times 10 to the minus 4 grams.